After watching this lecture, you will be able to understand why alkanes are less reactive, oxidation of alkanes in the presence of excessive oxygen, oxidation of alkanes in the presence of limited oxygen, oxidation of alkanes in the presence of very limited oxygen, the complete free radical mechanism of oxidation of alkanes, the reactivity order of primary, secondary and tertiary alkanes toward oxidation, how carbon monoxide is produced and why it is dangerous for human beings, what syngas is, and why it is important what octane number is and why it is important in fuels. If you find this lecture helpful, then please like, share, and subscribe to the YouTube channel Chemistry Support for more conceptual chemistry lectures. So students, let us start the lecture. Okay, look at this molecule. Carbon, hydrogen, that is it. No double bonds, no oxygen, no functional group, just carbon and hydrogen, fully saturated. This is an alkane. And your first question should be, can we oxidize this thing? Let us find out. First thing, take KMO4, strong oxidizing agent. Pour it onto an alkane. Nothing happens. Take a strong acid. Nothing. Strong base. Nothing. Why? Because look at the structure. Every carbon is bonded to the maximum possible hydrogens. There are no pi bonds, no lone pairs, no partial charges. A reagent needs something to attack. There is nothing here to attack. That is why alkanes are called paraffins, paramaffinis. Little affinity. They simply do not react. But here is the key question. If they do not react with strong reagents, how do we oxidize them at all? The answer is oxygen and heat. Complete combustion. This is the most extreme oxidation possible. Look at methane. CH4. Carbon is at oxidation state -4. After combustion, carbon becomes CO2. Oxidation state +4, that is a change of 8 units in one reaction. Every single CH bond breaks. Maximum energy release. The equation is simple. CH4 plus 2O2 gives CO2 plus 2H2O. Energy released is 890 kilojoules per mole. Now write octane. C8H18, the equation becomes 2C8H18 plus 25O2 gives 16 CO2 plus 18H2O. Over 5,000 kilojoules per mole. That is petrol burning in your car engine. Now the important question. What if oxygen supply is restricted? This is where it gets serious. 3 scenarios. Write these down. Excess oxygen. Complete combustion. Products are CO2 and H2O. This is ideal. Limited oxygen. Incomplete combustion. Product is CO, carbon monoxide, not CO2. Carbon only gets partially oxidized. Very limited oxygen. Product is just C carbon particles. Black soot. You have seen this on a candle flame. Now why does carbon monoxide matter? Because CO binds to hemoglobin 200 times more strongly than oxygen does. Your blood picks it up instead of oxygen and stops functioning. This is why exhaust fumes in a closed garage kill you. This is why catalytic converters exist. Their job is to take that CO from the exhaust and oxidize it to CO2 before it leaves the pipe. Now I want you to think about this carefully. Combustion takes alkane all the way to CO2. But can we stop the oxidation halfway and get something useful? Yes, and this is how industry makes billions. Think of oxidation as a ladder. Each rung is a higher oxidation state of carbon. Bottom rung, alkane, carbon at -2 to -4. Next rung, alcohol, carbon at -1. Next rung, aldehyde or ketone, carbon at 0 to +1. Next rung, carboxylic acid, carbon at +3. Top rung, CO2, carbon at +4. Fully oxidized. Game over. Combustion jumps straight to the top. Industry wants to stop at rung 2 or 3 because those are valuable chemicals. The challenge is always the same. How do you stop the reaction before it overshoots? The answer is the right catalyst at the right temperature. Right, now we understand what oxidation does. Let us understand how it actually happens. The mechanism. Alkane oxidation goes through a free radical chain mechanism. 3 stages. Learn these perfectly. Stage 1. Initiation. Heat breaks the O bond in oxygen homolytically. Each oxygen atom takes one electron. You get two oxygen radicals, O dot. These are extremely reactive species with unpaired electrons. Stage 2. Propagation. The oxygen radical attacks a CH bond. It pulls off a hydrogen atom. Now you have an alkyl radical, R dot. That alkyl radical attacks an oxygen molecule, forms a peroxy radical. That peroxy radical pulls a hydrogen off another alkane molecule. New alkyl radical forms. New cycle begins. This is the key point. One initiation event creates thousands of propagation cycles. The chain multiplies itself. That is why combustion is explosive once it starts. The energy release is not from one reaction. It is from thousands of chain cycles happening simultaneously. Stage 3. Termination. Two radicals collide and pair their electrons. Chain stops. R dot plus R dot gives RR, or HO dot plus R dot gives RO. Now, one important detail about where the radical attack begins. Look at a branched alkane. You have primary CH bonds, secondary CH bonds, and tertiary CH bonds. Which one gets attacked first? Tertiary. Always tertiary. Two reasons. One, tertiary CH bond energy is about 400 kilojoules per mole. Primary is 420. Tertiary is weaker, easier to break. Two, the tertiary radical that forms is more stable. Three alkyl groups around it donate electron density and stabilize the unpaired electron. More stable radical forms faster and lasts longer. So radical attack starts at tertiary carbons. This matters for understanding selectivity in partial oxidation reactions. Now, industrial applications. 3 reactions every student must know. First, steam reforming of methane, CH4 plus H2O at 800 degrees Celsius over a nickel catalyst gives CO plus 3H2. This mixture is called syngas. From syngas, you make ammonia for fertilizers. You make methanol. You make synthetic diesel through Fischer-Tropsch process. This single reaction feeds half the world through the fertilizers it produces. Second, butane to maleic anhydride. 2C4H10 plus 7O2 over vanadium pentoxide catalyst at 400 degrees gives maleic anhydride plus water. Butane is cheap. Maleic anhydride is used in polyester resins and plastics. The vanadium catalyst holds the oxidation exactly at this point. Without it, butane just burns to CO2 completely. Critical point for all 3. The product is more reactive than the starting alkane. Methanol oxidizes more easily than methane. Formaldehyde oxidizes more easily than methanol. So the moment your product forms, it wants to keep reacting. Industrial reactors quench the reaction gases within milliseconds to freeze the product at the right rung of that ladder. Last concept. Octane rating. The compression itself heats the mixture enough to start the radical chain reaction before the spark. 2 flame fronts form inside the cylinder. They collide. Violent pressure spike. That metallic knocking sound from an engine. That is uncontrolled radical chain combustion. It wastes energy and damages the engine. Now, which alkanes knock badly? Straight chain alkanes. Which alkanes resist knock? Branched alkanes. Isooctane, 2,2,4-trimethylpentane. The branching creates steric bulk around the CH bonds. The radical chain cannot propagate freely. It resists premature ignition. Knock rating of 100. Best possible. So the octane number on the petrol pump is literally telling you the percentage of isooctane in an equivalent reference mixture. 95 octane petrol behaves like 95% isooctane and 5% N-heptane.